We've spent our time in studying linear and angular kinematics as separate entities. And it's way important that in our applied biomechanics, in other words, using the physics of movement, the knowledge of that science in how we coach people or how we train people or how we interpret movement. Well, the beginning of that is to say, okay, the interplay between linear and angular. Here's an example. And this has to do with displacement. Displacement equals theta, or the angle of movement, right? This angle of movement is held constant. Wherever you put your protractor or your goniometer, you're going to get the same angle. The displacement is greater where the radius of rotation is longest. The linear displacement is greater. Here's a shorter radius, the displacement is different. And so what is the application of this? So to interpret this, displacement equals theta times radius. You're going to have a bigger d if you have an angle times a longer radius. A way to look at this is, if for our consideration the angle is held constant, the farther you are away on the bat, the greater the displacement. Well, what's the application? For a baseball or a softball hitter, the longer bat that you use, the greater linear displacement. And so in baseball parlance, you can cover the outside part of the plate because you have greater linear displacement. Another example of that would be in the activity of pole vault. Obviously, you've got to have long enough pole given a theta that stays constant in order to have the appropriate displacement to get over the bar. If you're trying to clear 10 feet and you have an 8-foot pole, the physics of that don't work out very well. And so you have to have a pole that has a commensurate radius for your desired goal for getting over the bar. Now there's lots more mechanical properties in this in terms of displacing the pole in such a way that it stores energy to catapult up and over, but that's not our point at this stage. Appreciate the fact that the interplay between linear and angular on displacement is, if you're operating within a certain angle, if you increase the radius, you'll have bigger displacement. And then we move into the relationship of length of lever, r, and omega, angular velocity. If both of these quantities are very large, if you have a long implement or a body part and it's moving very quickly, the linear velocity will be very high. If you have a long bat and it's moving angularly very fast, you're going to have big velocity at the end of the lever. That hits the ball and the ball will be accelerated and ultimately have greater velocity. So that's way important in striking sports. Appreciate that the longer the bat, the greater velocity at the end of the bat. Well, so let's be ridiculous to make the point. Why wouldn't I go to the plate with this log? If this is in case, if this is the kinematic reality, why wouldn't I go way extreme on the R? Well, obviously, if we tried to move this as our bat, we would have 0 angular velocity. So it has to be within our capacity, again in baseball parlance, to manage the bat. If I am able to maximally achieve an angular velocity with a bat, let's say, that's 33 inches long, then I keep this quantity high, omega, and the limitations or the advantages of a bat that long. I can handle a bat that long, I can move it that fast angularly, therefore I'm going to have large linear velocity. Well, that's manipulating the R. How about manipulating the angular velocity. An example of that is the slap shot in ice hockey. He wants to have a good long stick, and the way he grips it, it needs to be a long lever, so R is big. But the deal is, when you played ice hockey, or people who are being trained in ice hockey now, when you do the slap shot, the idea is to move violently. This needs to be a ballistic delivery, so that you have a velocity that's imparted to the puck such that the goalie can't respond to it, can't make the glove save or the stick save or the pad save because it's whistling by his right shoulder and he doesn't ever see it. So the emphasis is be big, be as big as you possibly can be in the lever, and as fast as you can be. Another example is in this particular sport setting where this athlete, at the moment that she strikes the ball, she needs to be very long in her lever. This is her R, her radius. Now, she's already contacted the ball here, and it's coming off. She didn't start with this big old long lever. She didn't come back here like a bowler in cricket. She didn't do this. She moved to this position and then quickly got to an extended lever, and at the moment that she struck the ball, she had a long lever with very high angular velocity. That results in very large linear velocity that then accelerates the ball. The ball takes on a quantity of linear velocity. Got to have just exactly the right length of lever, and you need to be moving very, very fast angularly. Another example of this would be if we compare the hook punch in boxing. In order to really be successful, this is a knockout punch. We're operating under these same guidelines. Have a long lever and be moving very fast. But the preliminary delivery of this, it takes time to get cocked back and move here. So this doesn't get to the opponent very fast. If we consider the jab, the emphasis is on being quick, having very large angular velocity. In order to have large angular velocity, you need to have big linear velocity, but you need to have very short radius. So a small denominator and a large numerator results in a very high quotient. In this particular case, be quick. So the jab is thrown there, as opposed to a hook that takes time to get there. Now, I'll be quick with you on the hook. It's not like it's slow, but it doesn't get delivered as rapidly as the jab, because the radius, I'll say it another way, the premium is on having large angular velocity, so you can throw more jabs per unit of time. The way to do that is to have big velocity. You create internal force through the contraction of your muscles, but to have very short levers. Now, an example of that is if a volleyball team is receiving, everyone gets down into an athletic position, and they have very short levers because they've got to be quick to the ball. They might need to go up, they might need to go down, they might need to dive here, up, front, back. So the athletic position is comprised of many short levers. So the R, the denominator, is very small, and their linear velocity is high because they need to move quickly or to have large angular velocity. And then, do you remember, the last spring and summer, there were just so many fruit flies here on campus, and I didn't have good success at killing those if I had this really long lever, where I have this long lever. It takes me a long time to get there, and I have big killing force once I get there, but it took me too long because they're quick. And so what I needed to do was they have very short levers. And be quick, and be quick, and be quick, as opposed to powerful and slow. So when there's a premium on angular velocity, we need to have short levers. That's why in the David and Goliath circumstances of life, the giant is at a disadvantage because they can generate great force, but they're not as quick. There's a reason that there's not 8-foot tall point guards in the NBA. Now there's some very tall people who play guard because of unique set of circumstances. They're very, very special. But little people who are quick, they have shorter levers. Their denominator is smaller. So there's my example of the fruit fly. I can use a fly swatter this big because I can be quicker with a short fly swatter. But if I've got a real monster of a bug to kill, I need to have something with greater killing force, which means it's going to be longer. Yeah, the emphasis is on big velocity. He's not so quick, so I don't have to be so quick. I still have to be quick, but the emphasis is on a longer lever. I'd like you to think about, for class, applications of these two interplays in the world in which you work. I wish I'd said at the beginning of this video that the PowerPoint available to you on eClass includes these slides, and you certainly can help yourself. Ask you a couple of questions. Here are two really great hitters. This man is playing in the World Series right now. This man played a long time for Seattle Mariners and played for the Yankees in the American League Championship Series. Their approach to hitting is way different, and I've circled their back foot to indicate how different their approach is. This back foot isn't weight bearing at this point. Excuse me. Yeah, this man is not weight bearing. He's really started to run before he hits the ball, as opposed to this man who everything is happening here. If you look how long the levers of his arms are, they're very short. He's flexed in the elbows, as opposed to this man who's got a very long lever, very long lever. He's built for linear velocity. He's built for angular velocity. So put that in the hopper. Be students of the interplay between linear and angular velocity and displacement. Okay, bless you guys. See ya.